We build AI factories with 800 gigabit per second physical links and highly optimized compute kernels. These facilities operate at extreme physical capacities. Yet, like a massive array of perfectly synchronized mechanical rotors, if one microscopic gear seizes, the entire system shudders and halts. Despite those raw hardware speeds, operators consistently see expensive accelerator clusters suffering from debilitating idle times. The individual components are fast, but the total time it takes to complete a job continues to lag. The metric for performance has shifted. We can no longer measure efficiency by the output of a single accelerator. We have to measure the completion of a distributed execution graph. Completion time is a critical path equation, the sum of compute, collective operations, queuing delay, state transfer, and policy checks. Notice the network queue and storage terms. As the queuing variable expands, downstream compute nodes are forced to wait, leaving GPUs idle and inactive. Because these variables are chained together, tuning a single component in isolation fails. Making a compute kernel faster yields zero benefit if the global system is stalled by a congested network path. To handle network traffic, data centers rely on explicit congestion notification, ECN, and priority flow control, PFC. Both of these mechanisms operate on lagging indicators. They only generate signals to throttle traffic or pause classes after a queue has already formed, or worse, after packets are actively dropping. Equal-cost multipath routing distributes these flows, but it hashes them blindly. It maps traffic to available paths without any visibility into the upcoming structure of an AI workload. Agentic AI workloads break this traditional routing logic. They generate massive, variable-length dependency graphs that triggers sudden fan-out microbursts to external tools and memory stores. When these microbursts hit the network, a reactive, flow-blind pause signal cannot distinguish between a critical planner branch and a low-priority background task. It halts everything indiscriminately. The alternative is anticipatory cross-layer coordination. Tensor Networks formalized this approach with the Predictive Tensor Control Plane, or PTCP. PTCP ingests workload intent. It reads the schedule of upcoming operations to act on leading indicators, pre-positioning resources before network congestion even occurs. Reacting to congestion in AI workloads guarantees wasted accelerator cycles. The mathematical reality is that you must predict and prevent the bottleneck before the queue forms. This physical routing problem is highly visible in Mixture-of-Experts, or MOE models. An MOE layer routes specific tokens to specialized subset networks, activating only a fraction of the total parameters per token. While this sparsity saves compute, it converts that saved effort into massive all-to-all network communication. The tokens must be physically dispatched across the cluster and later combined. This dynamic routing creates unequal token distribution. A specific prompt can immediately surge demand for a single domain, resulting in an overloaded hot expert. This diagram shows the reactive fabric state. The thick red line represents an incast bottleneck forming at a single expert node. By the time the congestion signal travels backward from the overwhelmed port, the damage is done. Hot experts, incast, and idle accelerators. This triggers straggler amplification. A collective synchronization barrier requires every rank to finish before moving on. The slowest individual rank dictates the completion time for the entire cluster. A minor P99 tail delay on a single network link cascades instantly. It forces thousands of GPUs to wait, translating directly into thousands of dollars of wasted compute cycles per hour. PTCP operates under a strict architectural rule. Cross-layer intelligence must never become an unbounded dependency on the fast path. This flowchart details PTCP's dual-loop architecture. The observation plane up top normalizes multi-domain telemetry. The left predictive slow path forecasts demand, sending candidate actions to the central policy gate for strict security checks. Approved policies then hit the right deterministic fast path for line rate execution. By isolating prediction to a separate slow path, PTCP secures cluster-wide coordination while maintaining the deterministic microsecond enforcement that AI workloads require. We can apply this architecture directly back to the MOE all-to-all incast bottleneck, replacing the reactive transport response with coordinated anticipatory control. Long before the actual tokens are dispatched across the network, the slow path ingests the scheduled NCCL collective map. It knows exactly where the traffic is going to surge. This diagram shows the PTCP assisted fabric on the right. Based on the forecast, the controller deploys an expert replica, shown here as E1 prime, and distributes path intent across multiple routes to absorb the incoming burst. Preconditioning the network eliminates the incast peak entirely. Anticipating the load and spreading it out yields higher goodput, than waiting for a crisis and executing a flawless reactive pause. A common misconception in AI infrastructure is that eliminating network bottlenecks requires ripping out existing hardware to install proprietary fabrics like InfiniBand. PTCP is designed as a software control overlay. It deploys directly onto brownfield, common Ethernet environments to extract more useful work from existing assets. This diagram shows where PTCP sits, a control overlay operating globally. It doesn't replace communication libraries. NCCL still executes GPU collectives, while PTCP supplies path constraints. Below, the foundational Ethernet data plane remains unchanged, executing policies using standard IP and RockV2 without custom hardware. Achieving maximum AI performance does not mandate proprietary greenfield hardware. It requires a vendor-neutral policy layer capable of orchestrating the mixed infrastructure you already have. Tuning an isolated component often pushes the bottleneck somewhere else. Making a compute kernel run faster yields no benefit if it immediately collides with uncoordinated storage or KV cache traffic. The ultimate metric for AI infrastructure is not the line rate of a single port. It is total job completion time and the volume of accepted tokens per dollar spent. This chart outlines PTCP's evidence-gated deployment model. Moving from baseline observation through advisory and scaling, it demands hard validation. Focusing on the canary phase, it limits blast radius, deploying policies on a strict traffic subset to establish causality and guarantee unaffected workloads don't regress. In an environment where tail latencies dictate facility economics, raw physical speed has a ceiling. The real competitive advantage belongs to the infrastructure that can predict its own workload, securing both execution speed and capital efficiency on common Ethernet.